Okay, so in essentially the entire series so far, we've been dealing with different search strategies, different ways of ordering and ranking our nodes and choosing which ones to expand next. We've then also obviously moved towards A star, where we seem to be staying or at least building upon from here onwards. But I have obviously been talking throughout this about this idea of tie-breaking strategies. So a lot of these algorithms, of course, you have a bunch of nodes that are ranked the same. You're going to need some way to tie-break, to choose which of these we want to expand next. I think this also raises some questions. I have said that tie-breaking is important. So in this video, I just want to dive and write down a couple ideas of hey, some common ways that we might be able to do this. I think oftentimes we do use rather simple ones, which we've just seen to prove rather effective in generic practical performance. So I'm also going to, we're going to talk over a graph showing in a whole bunch of real-world benchmarks from the Grid Path Planning Competition, GPPC. So this is it's a pathfinding community challenge that is open to anyone in the world to apply and to submit their algorithms and rank up against everyone else. And so this is often announced and the results are reported at an international computer science conference called ICAPS, the International Conference for Automated Planning and Scheduling, obviously directly applicable to everything we're talking about. And so yeah, the GPPC has this entire suite of these public benchmarks and these public results that are published. So here I will show a plot of a whole series of different algorithms. So it's showing over an entire whole series of popular benchmarks. On the x-axis, we have essentially the number of nodes
generated.
Number of nodes that were necessary to
generate
in order to find the final solution, right? So this is how much work was necessary. Then on the y-axis, we actually have the number of nodes that had the same f value, right? So we're trying to see, well, in all these problems, how many of the problems actually was tie-breaking actually influential in? How many of the nodes were ranked the same? How much was this actually an important aspect of solving the problem? And so we see, right, that there's this very almost direct line on the 45-degree angle, right, which is essentially saying that in many of these domains, the large majority of all nodes that had to be expanded shared the same f values. So really we're saying that the large majority of all nodes were technically indistinguishable from each other in terms of f values, in terms of search order of expansion. So that's very interesting, right? I think that speaks directly to the idea that then the strategies that we can choose for tie-breaking has large potential to significantly impact the speed of our search algorithms. So with all of that said, then let's jump over here and let's try to jot down and discuss some basic ideas for how we can actually choose tie-breaking strategies. So I think one of the first ones that makes sense to write down are, right, like these very generic strategies. We can just try things, right, like hey, this was the first node that was added into my open list. I'm just going to use that one. I'm going to expand the first in, first out. Or how about the last one in, last in, first out. So these are our FIFO and LIFO queues. So I think these are very, very similar concepts to like either this depth-wise or breadth-wise expansion ordering. But this is definitely a valid approach to trying to choose a tie-breaking strategy. The idea, I think, is like oftentimes we really don't know, right? Like unless we as a human are dropped in, look at one specific problem, where we're going, where the walls are, what the topology of the map looks like. Maybe as humans, we would be able to create better heuristics. Just mentally, we would kind of know where you want to draw the line. But in terms of our algorithms and this general performance where our starting goal locations can be anywhere, any distance, it's really hard to come up with, like, obviously we'll never really be able to choose the best option every time. So we're going to have to just kind of come up with some rule-based method to try to do our best. So in that regard, what is, I think, easily the most common version of tie breaking, which is paired with the A-star algorithm, is this idea that we preference nodes that have the smallest heuristic value, right? So the smallest h value. So I think this is a very intuitive option, right, where we're essentially saying, hey, preference the nodes that we think are close to the goal. Hopefully your heuristic is relatively accurate. Instead of exploring nodes completely on the other side of the search space, hey, surely just try to deal with the ones that are close to the goal. Surely one of those will be able to reach it. Sometimes, of course, it doesn't, but that seems like a pretty good overall strategy. So we will call this essentially, so lowest h, so the lowest heuristic value, which is essentially equivalent, right, to essentially highest g as well. So it's the exact same thing. So the nodes that are the closest to the goals, in terms of f equals g plus h, will also, of course, be the nodes that have progressed the furthest away. Their cost so far is high. So this often proves a very efficient tie-breaking strategy in practice. Pretty much uniformly in a lot of basic A-star implementations. This is, especially just for like pathfinding on grids and things like this, this is often just the tie-breaking strategy that's employed. Now what's interesting to note, right, is when we break ties, it's not just you choose one strategy. Because once you break some ties, if we break the ties based on lowest heuristic, okay, well there's probably still going to be a large number of nodes on that frontier that also still share the same g cost, the same h cost. And so then, of course, there's always going to be this idea of like subsequent tie breaking. How many strategies you want to employ is up to you. I think the really, really standard, simple way to do this is often just, hey, in A-star, we choose based on the closest to the goal. Then the second strategy is the third one in our list, random tie breaking. Okay, random. So this one I think is really interesting to talk about, and I think is at first counterintuitive. When I ask you, hey, how do you think, come up with a strategy to do something, which of these do you think is going to be best? I think as humans it feels silly, right? Like intuitively this should perform poorly. If we just make random choices, we obviously didn't use any knowledge to inform us about which one we think. We're selecting it at random. On top of that, right, it means that your algorithms will no longer be deterministic. Based, I guess you can have like a random seed, and then you can obviously repeat it. But it introduces this idea of essentially inconsistency in the performance and search trace of our algorithms. Give me a different problem. Hey, I'm going to essentially, my tie breaking might change. I might do worse. I could do much worse. Sure, I could do better as well. Yeah, so that seems a bit odd. But what I'm here to convince you of, actually, is that random tie breaking is fundamental and fundamentally important to a lot of the practical performance of our algorithms. So it's not often picked first. I think in the A-star algorithm route, we still like this idea of the heuristic. But some form of random tie breaking or random shuffling is actually a common tactic in almost all state of the art. So why is this so efficient? Well, it means our algorithms are more robust to changes, but essentially it all boils down to this idea of guaranteeing performance or some threshold of performance. So what is maybe not immediately apparent is any time we choose some rule-based method, right? Well, that rule is applied every single time. It could be the worst thing you can do in a maze if you just choose to tie break with the direction that goes left every single time, or the leftmost node. You could end up doing the exact worst thing every time. The time it takes you to solve the problem can be orders of magnitude slower than your average performance. Worst cases are usually very, very bad. The search spaces and the size of them that we explore, if you're not doing well enough, if you really have to exhaustively, if you have to exhaust entire subtrees of this thing, in the worst case, you're exhausting all subtrees. That is really bad. So in terms of real-world applications, let's consider something like video games. There was this really great talk I watched at the Game Developers Conference, GDC. So they often publish a lot of the presentations to their YouTube channel, which is great. And I remember this one stuck with me from one of the Battlefield developers, where they're talking about essentially the expectations of their players and guaranteeing performance in essentially their pathfinding. So if you instruct your guy to walk somewhere to the other side, and then they get stuck, imagine they clip out of the nav mesh, they get stuck in a rock, and they can't move, they fall through the floor, maybe they fall out of the map. These worst cases are the bits that destroy your experience as a player. When we're trying to guarantee a specific threshold, a level, a guarantee, a minimum expectation, a minimum threshold of acceptable behavior in our algorithms, players often don't care if they take a very slightly suboptimal route, right? Or they take a little bit longer. Oh, instead of 20 milliseconds, it took 60 milliseconds. Those kind of things are not noticeable to the player. Whereas if you issue a movement command and your player stands still for a whole second, right, in this worst case situation, and if that happens often or consistently, well, then it destroys your performance, it destroys your experience, it destroys your immersion. So what I'm trying to say here is that the worst case is really bad, and it is the thing we want to avoid the most. We don't care if our algorithm does just okay more often than not. This is much better than ever doing really, really poorly. So how does random tie breaking come into this? Well, we're more robust to this because we don't always do the same thing. Even though we could have worse performance, so you never get stuck in the worst case. So I think that's really counterintuitive. Random tie breaking might sound silly, might sound super simple, really dumb, but in practice it performs very well. And so we'll see as well that in these really, really cutting edge, state-of-the-art multi-agent pathfinding systems, things like large neighborhood search, these are the forerunners in solving hard multi-agent problems. All of these as well really rely on this idea of building in randomness to our algorithms so that we can iteratively improve and iteratively escape local minima, right? We in our landscape of where we can get stuck, the worst case is always bad. We want some form of exploration, and we'll probably do okay. So I think that's all I want to talk about in this video. Here are some common tie-breaking strategies. There's other fun things you can do. You can come up with this based on anything that you choose, right? Because the tie-breaking is only impacting the performance, you are free to explore any method of doing so. But I think what's interesting is that in A-star, we often just go with, hey, we think we're close to the goal, and then we do things randomly. So thanks for watching, and let's continue into the next video where we start dealing with these ideas of guaranteeing performance, guaranteeing the optimal version of a path. Hey, sometimes it isn't always necessary to give me the exact optimal path. Well, how about we get close? So join me where I start talking about the idea of suboptimality. Thanks.